Welcome to this coding walkthrough. In this session, we'll dive into LeetCode problem number 388, titled Longest Absolute File Path. This is an interesting problem that involves parsing and reconstructing file system hierarchies from a string representation. Let's explore the solution and break it down step by step. In this problem, you are tasked with analyzing a string input that represents a file system in a simulated format. The string uses special characters to define the structure of the file system. Specifically, newline characters, represented as \n, separate different directories and files, while tab characters, represented as \t, indicate the depth or level of each item within the hierarchy. For example, a directory at the root level has no preceding tabs, whereas subdirectories or files nested inside it will have one or more tabs depending on their depth. A key distinction is that files always include a dot followed by an extension, such as file.txt, whereas directories do not contain dots. Your task is to determine the length of the longest absolute path to a file in this hierarchy. The absolute path length includes the combined lengths of all directories and files in the path, as well as one // for each separator between directories or files. If the string does not contain any files, the result should simply be 0. The input to this problem is a single string input, which has a length between 1 and 10,000 characters. This string can include lowercase letters, numbers, dots, slashes, spaces, and special characters like \n and \t that represent the structure of the file system. Your goal is to output an integer representing the length of the longest absolute path to a file. Let's look at an example to clarify. Suppose the input is a string representing this structure, dir \n subdir1 \n subdir2 n t file.ext. The output for this input would be 20. This is because the longest absolute path to a file is dir subdir2 file.ext, which has a length of 20 when you account for the lengths of the directory names, file name, and the slashes between them. To understand why the output is 20 in the previous example, let's break down the structure. The file system starts with the root directory dir. Inside dir, there are two subdirectories, subdir1 and subdir2. Nested inside subdir2 is a file named file.ext. The absolute path to this file is dir subdir2 file.ext. The length of this path is calculated by adding the lengths of dir, 3, subdir2, 8, and file.ext, 8, along with two slashes separating these components. Adding these together gives us a total of 20. Now, consider another example. If the input is a \n file1.txt \n /longfile2.txt, the output would be 18. The longest path here is a /longfile2.txt, with a total length of 18. This includes the length of a1 longfile2.txt, 12, and 1/. Let's now explore the second example in more detail. The file system starts with a root directory named A. Inside this directory, there are two files, file1.txt and longfile2.txt. The absolute path to longfile2.txt, which is the longest path to a file in this example, is a /longfile2.txt. The length of this path is calculated as follows. The root directory A has a length of 1, the file name longfile2.txt has a length of 12, and the / separating them adds another 1. Combining these values gives us a total path length of 18. Now, consider an alternative scenario where the input string is dir \n subdir1 \n subdir2. In this case, there are no files in the file system, only directories. As a result, the output is 0, because there is no path to any file. For the third example, the input string represents a file system with a root directory dir that contains two subdirectories, subdir1 and subdir2. There are no files present in this structure, which means there is no absolute path to compute. Without any files in the input, the problem specifies that the output should be 0. It is important to note that the constraints of the problem ensure that all paths in the input are valid, meaning we do not need to handle invalid or malformed file systems. Additionally, each directory or file name will have a maximum length of 255 characters, and the depth of the hierarchy will not exceed 100 levels. These constraints ensure we can process even deeply nested structures efficiently. Finally, let's consider a more complex scenario with deeply nested directories. Suppose the input string represents the following structure: a \n \ta \n \t ta \n t ta.ext. Here, we have a root directory A, which contains a subdirectory A, which in turn contains another subdirectory A, and finally, a file named a.ext nested deeply inside. The longest absolute path to a file in this case is a/a/a/a.ext. The length of this path is calculated by adding the lengths of each directory and the file name, as well as the slashes separating them. This level of nesting demonstrates the importance of handling varying depths and ensuring that the solution can manage large inputs efficiently. Additionally, the problem requires handling cases with mixed file and directory names, varying lengths, and irregular indentation patterns, all while ensuring correctness and optimal performance. To begin, let's consider the brute force approach, which is a straightforward but less efficient method. The idea here is to parse the input string line by line, identifying the depth of each file or directory by counting the number of tab characters. For each line, we manually construct the absolute path by concatenating the parent directories up to the current file or directory. If the line represents a file, which we can identify by the presence of a dot in its name, we calculate the length of the full path and keep track of the maximum length encountered. A few key observations are critical here. The depth of a file or directory is determined by the number of tab characters, files are distinguishable by their extensions, and we need to track the length of paths at each depth to efficiently build absolute paths. However, this approach quickly becomes inefficient as constructing paths involves repeated string concatenations, which can take quadratic time in the worst case. While simple to understand, this method is impractical for large inputs due to its high computational cost. Now, let's explore a more efficient solution with the optimized stack-based approach. This method leverages a stack to maintain cumulative path lengths for directories at each depth, eliminating the need for repeated string concatenations. The process involves counting the number of tab characters to determine the depth of the current file or directory. If the depth is smaller than the stack size, we pop elements from the stack to backtrack to the correct parent directory. For a new line, we compute the cumulative length by adding the current directory or file's length to its parent's cumulative length stored in the stack. If the line represents a file, we use this cumulative length to update the maximum path length. This approach is efficient because the stack allows for constant time backtracking, and storing cumulative lengths avoids the overhead of repeatedly constructing full paths. Identifying files by the presence of a dot remains a key detail, ensuring that we only calculate path lengths for files. Analyzing the complexity of the stack-based approach, we see that it processes each character of the input string exactly once, resulting in a linear time complexity of O(n). The space complexity is proportional to the maximum depth of the file system since the stack grows and shrinks based on the directory depth, making it O(d). While this approach is slightly more complex to implement compared to brute force, it is significantly more efficient and scalable. There is also an alternative approach that uses recursive parsing to process the file system hierarchy. This method involves splitting the input into lines and recursively exploring each subtree to find the longest path. While elegant, recursion introduces additional overhead, such as the risk of stack overflow for deep hierarchies and the inefficiency of repeated substring operations. As a result, the recursive method, though intuitive, is less practical for large inputs compared to the optimized stack-based solution. Given the trade-offs, we chose the optimized stack-based approach as the most suitable strategy for this problem. This method avoids the inefficiencies of repeated string concatenations that plague the brute force approach and is more robust for large inputs than recursion, which risks stack overflow. The key insight lies in realizing that we don't need to explicitly construct full paths for files. By maintaining cumulative path lengths at each depth, we can calculate the length of any file's absolute path efficiently. The stack plays a crucial role in dynamically adjusting the parent directory as we process each line, ensuring correctness and efficiency. This approach achieves optimal time and space complexity, making it both elegant and practical for the constraints of this problem. In this problem, we are tasked with finding the length of the longest absolute path to a file in a file system that is represented as a string. Each line of the string corresponds to either a file or a directory, and the hierarchical structure is indicated by the number of tab characters at the start of each line. Files are identified by the presence of a period in their name, whereas directories do not contain periods. If the system contains no files, the result will simply be 0. The challenge lies in correctly interpreting this structure and calculating the longest path to any file within it. To solve this problem, we start by breaking it down into a series of clear steps. First, we parse the input string by splitting it into lines using the new line character as a delimiter. This gives us an array where each element represents either a file or a directory, while preserving their relative positions in the hierarchy. Next, we need some data structures to help us keep track of the information we process. A stack is used to store the cumulative lengths of directory paths at each level of the hierarchy. This allows us to dynamically manage the path lengths as we traverse the structure. Additionally, we maintain a variable called max_length, initialized to 0, which will be updated whenever we find a file with a longer absolute path. Now we process each line in the array. First, we determine the depth of the current line by counting the number of leading tab characters. The depth tells us how deeply nested the current file or directory is. We then remove these tab characters to isolate the name. To ensure the stack reflects the current hierarchy, we pop elements from it if its size exceeds the current depth, effectively moving back to the parent directory. Once the stack is adjusted, we calculate the cumulative length of the current path. If the stack is empty, the length is simply the length of the current name. Otherwise, we add the length of the current name to the top value of the stack, along with one additional character for the separator. This updated length is then pushed onto the stack, keeping our hierarchy intact. If the current line represents a file, which we identify by checking for a period in its name, we compare the current path length to max_length and update max_length if the current length is greater. After processing all lines in the input, the solution is straightforward. We simply return the value of max_length. This value represents the length of the longest absolute path to a file in the system. There are several key insights that make this approach efficient. First, using a stack allows us to manage the hierarchy dynamically, ensuring that we always have the correct cumulative path lengths for the current depth. When the depth decreases, we pop elements from the stack, effectively moving up the hierarchy. Second, the calculation of path lengths is efficient because we only add the current name's length to the cumulative length of its parent directory. Finally, distinguishing files from directories using the presence of a period ensures that we only update max_length when we encounter a file. This solution relies on two main components, the stack and the variables we use to track the solution. The stack is the backbone of our hierarchy management, storing cumulative path lengths at each depth and allowing efficient push and pop operations to adjust as the hierarchy changes. The variable max_length is essential for keeping track of the longest absolute path we encounter. In terms of complexity, the algorithm is highly efficient. Splitting the input string into lines takes O(n), where n is the length of the input. Iterating through the lines and performing stack operations is also O(n), making the overall time complexity O(n). Space complexity is proportional to the maximum depth of the file system, as the stack grows in size based on the depth. This gives us a space complexity of O(d), where d is the maximum depth of the hierarchy. This solution is designed to calculate the length of the longest absolute file path in a given string representation of a file system. The implementation uses a dictionary to store cumulative path lengths at different depth levels and iterates through each line of the input string to process files and directories. First, we initialize a dictionary path_length with a base case. At depth 0, the cumulative path length is 0. We also initialize max_length to 0, which will store the maximum path length found during the traversal. The input string is split into lines using split \n, allowing us to process each file or directory individually. For each line, we count the number of tab characters \t to determine its depth in the directory structure. The depth indicates how deep the file or directory is nested. Then, we remove all leading tabs using strip \t to extract the actual name of the file or directory. If the current name contains a dot, it is identified as a file. The absolute path length to this file is calculated by adding the cumulative path length at the current depth, path_length, depth, and the length of the file name. If this calculated path length is greater than the current maximum, max_length, we update max_length. If the name does not contain a dot, it is a directory. In this case, we update the cumulative path length for the next depth level, depth plus 1, by adding the length of the directory name plus 1 for the trailing / in the path. After processing all lines, the maximum path length stored in max_length is returned. If no file exists in the input, max_length remains 0, which is the correct result for that case. This approach efficiently processes the input with a single pass and uses space proportional to the depth of the file system hierarchy, ensuring optimal performance. Here, we start by importing the necessary packages and defining our solution class. Inside it, we have the length longest path method, which takes a string input representing the file system structure. First, we create a map called pathLength to store the cumulative length of paths at each depth level. This map helps us keep track of the total length of the directory structure as we navigate through it. We initialize depth level 0 with a length of 0, since we start with no directories or files. Next, we define a variable maxLength to keep track of the longest absolute path we encounter. Now, we split the input string by new lines to process each file or directory individually. For each line, we calculate its depth level by counting the number of tab characters, which is done using last index of \t plus 1. This gives us the depth of the current file or directory. We then remove the tabs from the line to extract the actual name of the file or directory. If the name contains a dot, it indicates a file. In this case, we calculate the full path length to the file by adding its length to the cumulative path length at the current depth. We then update maxLength if this path length is greater than the current maximum. If it's a directory, we update the map to include the cumulative path length at the next depth level, adding the directory's name length plus 1 additional character for the trailing /. Finally, after processing all the lines, we return the value of maxLength. This variable holds the length of the longest absolute file path found in the given file system structure. By using the path length map to dynamically track cumulative lengths at each depth, we ensure that the solution is efficient and handles nested directories correctly. The method is now complete and ready to handle various file system input scenarios. Here, we begin with a simple file structure containing a directory called dir and a file named file.txt. To solve the problem, we initialize two variables, path_length as a dictionary with the key 0 set to 0, which will help us keep track of cumulative path lengths at each depth level, and max_length set to 0, which will store the length of the longest absolute file path encountered. Processing the first line, which is dir, we calculate its depth as 0 because it contains no tabs, and extract its name as dir. Since it's a directory, we update the cumulative path length at depth 1 by adding the length of dir, plus 1 for the trailing /. This gives us a new cumulative length of 4 at depth 1, and the path_length dictionary is updated to 0, 0, 1 and 4. Next, we process the second line, which is \file.txt. The depth here is 1, as there is one tab, and the name is extracted as file.txt. Since this is a file, we calculate the full path length by adding the cumulative path length at depth 1 to the length of file.txt. This gives us a total length of 12. We then update max_length to be the maximum of the current max_length and the calculated full path length, resulting in max_length being updated to 12. With no further lines to process, the final output for this example is max_length equals 12, which represents the length of the longest absolute path to a file. Moving on, we now explore a more complex example with nested directories and files. In this example, we have a directory structure with nested subdirectories and files. As before, we initialize path_length as 0, 0, and max_length as 0. Starting with the first line, dir, we determine its depth as 0 and its name as dir. We then update the cumulative path length at depth 1 to 4, and path_length is updated to 0, 0, 1 and 4. Next, we process the second line, \subdir1, with a depth of 1 and name subdir1. The cumulative path length for depth 2 is updated to 12, and the dictionary becomes 0, 0, 1, 4, 2, 12. For the third line, \t_file1.ext, which is at depth 2, we calculate the full path length by adding the cumulative length at depth 2 to the length of file1.ext. The full path length for file1.ext is calculated as 21, and we update max_length to 21, as it is now the longest file path encountered. Next, we process the fourth line, \subdir2, which is at depth 1 with the name subdir2. The cumulative path length at depth 2 is updated to 11, and the dictionary becomes 0, 0, 1, 4, to 11. Finally, for the fifth line, \t\file2.ext, at depth 2, we calculate the full path length as 20. Since this is less than the current max_length of 21, the value remains unchanged. The final output for this example is max_length equals 21, representing the longest absolute path to a file in this nested structure. In the final example, we examine a directory structure with no files, only directories. The initialization is the same, with path_length set to 0, 0, and max_length to 0. Processing the first line, dir, we update the cumulative path length at depth 1 to 4. Then, for the second line, \subdir1, at depth 1, the cumulative path length at depth 2 becomes 12. For the third line, \subdir2, also at depth 1, the cumulative path length at depth 2 is updated to 11. Since there are no files in this structure, max_length remains 0. The final output for this example is max_length equals 0, as there are no absolute file paths to consider. To analyze the time complexity of our algorithm, we start by breaking it into its key steps. First, the input string is split into individual lines using new line characters. If there are n lines in the input, this splitting operation takes n time. Then, for each line, we count the number of tab characters to determine its depth in the directory structure. This counting operation depends on the length of the line, and with L as the average length of a line, the total cost for all lines is n*L. Additionally, we use the strip operation to remove leading tabs and extract the file or directory name. Like tab counting, this operation also depends on the line length, contributing another n*L. For directory lines, we perform updates to a dictionary that tracks cumulative path lengths, which are constant time operations, adding n to our time complexity. Finally, for file lines, we compute their absolute path length and update the maximum path length, requiring string length calculations, which again contribute n*L. When we combine all these operations, the overall time complexity becomes n*L, where n is the number of lines in the input and L is the average length of each line. In the worst-case scenario, where the entire input is a single continuous string, L could grow proportionally to the total input size. Now, turning to space complexity, the algorithm's space usage can also be broken down. First, the input string itself is stored in memory, requiring OS space, where S is the total size of the input. Splitting the input into a list of lines adds another n, as there are n lines in the input. The dictionary that tracks cumulative path lengths uses space proportional to the depth of the directory structure. In the worst case, the depth is equal to the number of lines, which results in n space for the dictionary. In addition to the space used for the input in dictionary, a constant amount of space is used for auxiliary variables like max_length, depth, and name. When we sum these contributions, the total space complexity becomes s plus n, where s is the input size and n is the number of lines. In most cases, n is proportional to s, so we can simplify the space complexity to os. To compare, a naive approach to solving this problem might involve explicitly generating every possible file path and then checking their lengths. This would lead to an exponential time complexity of 2 to the power of n in the worst case, along with 2 to the power of n space to store all paths, making it highly inefficient. The optimized approach we use avoids this by dynamically tracking cumulative path lengths with a dictionary, reducing both time and space complexity significantly to n*L and s plus n, respectively. Examining the algorithm under different scenarios, the best case occurs when all lines represent shallow directories or short files with minimal L. Here, the time complexity is n, and the space complexity is os. In the average case, where we have a mix of files and directories with moderate nesting and average L, the time complexity is n*L, and the space complexity is s plus n. For the worst case, where the directory structure is deeply nested and L grows proportionally to the input size, the time complexity remains n*L, but the space complexity does not exceed s plus n. Mathematically, since the algorithm processes each line exactly once and the operations depend on the line length, the time complexity is n*L. Meanwhile, space usage is dominated by the input size in dictionary storage, resulting in O, S plus N. This balanced complexity makes the algorithm efficient for handling real-world scenarios. When solving the longest absolute file path problem, there are a few common mistakes to be aware of. First, not accounting for edge cases like an empty input, a single-level hierarchy, or a deeply nested structure can lead to unexpected runtime errors or incorrect results. It's essential to test your solution against these scenarios to ensure robustness. For example, an empty string or a single file should still return valid outputs. Another frequent issue is incorrectly parsing the indentation levels. The number of leading tabs or spaces in the input defines the hierarchy, so any misinterpretation here will result in an incorrect file system structure. Using a reliable method like line.count, \t, ensures that you correctly map each depth to its parent directory. Finally, overcomplicating the solution with recursion is a trap many fall into. While recursion might seem like a natural fit for hierarchical problems, it can lead to stack overflow for deeply nested inputs or make the code unnecessarily complex. Instead, an iterative approach using a stack is both efficient and simpler to manage in these cases. Another critical consideration is correctly resetting the path length when transitioning between sibling directories. If the path length isn't updated properly as you move up and down the hierarchy, your calculations for the longest path could be off. To handle this, use a stack to dynamically track the current path length, popping levels as needed when moving up in the directory tree. Additionally, it's important to distinguish between files and directories. Only files contribute to valid paths, so treating them the same can result in incorrect results. A simple way to differentiate is by checking for the presence of a dot in the name, which usually indicates a file. Paying attention to these details will help you avoid common pitfalls and produce accurate results. From an interview perspective, there are a few insights to keep in mind when tackling this problem. First, interviewers often want to see your ability to choose the right data structure. A stack is typically optimal for managing directory depths, and knowing why it's better than recursion can set you apart. It's also crucial to understand the input-output expectations clearly. For example, confirm whether the input uses tab-based indentation and whether the goal is to find the longest path or something else, like all valid paths. Optimizing space usage is another key point. Iterative solutions with a stack are generally more space efficient than recursive ones, which risk stack overflow for deeply nested directories. And, of course, edge cases always matter, so be sure to test your solution against scenarios like no files, a single directory with multiple files, or very deep hierarchies. This problem shares similarities with several others on LeetCode. For instance, problem 17, letter combinations of a phone number, also requires navigating a tree-like structure using recursion or iteration. Problem 22, generate parentheses, involves constructing valid combinations with hierarchical constraints, which is conceptually similar to building paths in a directory. Problem 71, simplify path, deals with parsing and navigating a path-like string, making it another relevant comparison. And problem 339, nested list weight sum, focuses on traversing nested structures to calculate a specific value, much like calculating the longest path in a file system. In terms of alternative approaches, recursive DFS is a simpler method to implement but comes with the trade-off of higher space complexity and the risk of stack overflow in deeply nested cases. Iterative solutions using a stack are more space efficient and avoid recursion, though they can be slightly more complex to write. Another option is using a hash map to store the current path length at each depth, which can be efficient but may feel less intuitive compared to a stack for some candidates. Choosing the right approach depends on the constraints and the problem's requirements. Thank you for joining me in solving LeetCode problem number 388, longest absolute file path. We covered the brute force approach and its key insights. Remember to practice similar problems to enhance your understanding of hierarchical data structures. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!